Well, thank you, Nick, and thank you all for being here. I'm really excited to tell you what I've been up to for the past 6 or so years. So I wanted to start with a bit of a story. So back when I was a young computer scientist in middle school, I was really into downloading movies. And there was this one time my dad yelled from the other room, "Hey, Bruce, quit hogging all the bandwidth." And I was like, no way, I'm not hogging all the bandwidth. Everyone knows computers figure out this for themselves. And maybe I use this argument, maybe I use that argument. And he was like, well, that's all great, but the internet isn't working. Can you please cut it out? And I was like, sure. And so I stopped downloading the video, and like, sure enough, things started working well. But so this seems like a tragedy for me because I don't get to watch this video. But really what I wanted to do was watch the video the next day after school. And so I could just download the video the next day when no one was home, and everyone in this situation could get what they wanted out of the internet. And so there's a moral here, and the moral is that the internet is a shared resource. There are things one application can do to be friendlier or less friendly to all of the neighboring applications that are using the same networks. So this is what my thesis is about. There's 3 different chapters to it. The first one is about smoothing out video traffic to make it a friendlier neighbor. The second one is about running experiments in congested networks. And then the last one is about sizing buffers and routers, which we're not going to talk about today. So here's the first work about smoothing video traffic. This is joint work with Shravya, Renata, TY, Grenville, Ramesh, and Nick. Thanks for being here today. And we are submitting it to SIGCOMM this year. So we look at video traffic in this paper, and the reason we look at video traffic is because video traffic is the majority of the internet today. So estimates range depending on where you are in the world. It's somewhere between 65 and 75% of all of the bytes sent on the internet last year were just video. This is because video is very popular and it's also relatively large. So let's watch a video. So here's a video, which I have to mute. Great. So this video is about Sammy the snail. And so Sammy's walking here on a plate and he's about to walk off the plate. So I wanted to point out a couple of things about the video, which you know because you've watched video before online. So one is this red point here. Got to do this on the screen. The red point here. This is where we are in the video right now. This is moving forward at 1 second every second, and it's moving forward smoothly. Over here to the right, this light gray bar, which just finished up downloading the entire video. This is called the buffer. This is how much of the video we've downloaded now. And so if the internet went away right now, we could still watch to the end of the video without any interruptions. So now I want to point out something which you might not know, which is that video traffic is bursty. So what I want you to do is I want you to watch that light gray bar, and it's going to grow quickly over time. It's not going to grow smoothly at 1 second every second. Great. So the video just shot up the buffer, and now it's paused for a bit. It shoots up again, and then a little bit, and then it'll shoot up a lot. And so it's growing in this bursty kind of way. So let me show this to you in another way. So here's 2 graphs. The graph on the left is the size of the buffer while we're watching the video. The graph on the right, this is the throughput. This is how fast we're downloading from the internet. And so what you're going to see on the right are these on periods, which are filled in when we're downloading quickly from the internet. And then these off periods where we're not downloading anything at all. When we look at the buffer is going to shoot up, and then it's going to drain slowly at 1 second every second. Great, so let's watch this. So the buffer shoots up, and now it's draining. And it's going to shoot up, and now it's draining. And it'll do this over and over again until we've downloaded the whole video. So this is like a well-known phenomena of video traffic. It's called the on-off behavior of video, and it's been observed since at least 2011. So why is video traffic bursty? So video is bursty because it's streamed at 2 different rates. There's the bit rate of the video. This is the rate that we watch video. So we watch video at 1 second every second. The video is encoded as bits, and so we're watching a certain number of bits every second. If you have more bits, you can represent more information, and the better the video is going to look. So over here on the left, we have a low bit rate, about 10 kilobits per second. Over on the right, we have a higher bit rate of about a megabit per second. It'll look a lot better. The other rate is the throughput. So this is the rate that we're downloading the video to our computer. So both of these are rates, and you have to give them some time scale. For the networking folks in the room, I want you to think about the time scale of about a chunk of video. For the non-networking folks, think about a couple of seconds or less than a second. So we've got these 2 rates here. They measure 2 different things, and they're chosen by 2 different algorithms. So the throughput are chosen by what are called congestion control algorithms. And this is a super classic area of networking research dating back to at least the 80s. The goal of these algorithms is to send as fast as possible without overloading the network, without sending too fast. The bitrate is what is chosen by adaptive bitrate, or ABR algorithms. The reason these algorithms exist is because congestion control algorithms can pick any throughput that they want. And if they pick a throughput slower than the bitrate of the video, then you are watching the video slower than you're downloading it. You're watching the video faster than you're downloading it. Great. And things are going to get worse. So for instance, here we are, we're watching the video, we're downloading it slower, and at some point we're going to run out of video to watch. The video is going to pause, and we're going to get that spinning rebuffer that we're all familiar with. But there's actually many ways that video traffic can get worse. So I want to introduce the idea of the quality of experience, or QoE, of the video. And this is measured by three major parts. So the first one is whether or not we have rebuffers, which we just saw. The next one is bitrate, which we were just talking about. And the last one is the play delay. This is how long it takes the video to start playing after you click play. So I've drawn a triangle here, and this is because you can actually trade off between all three different things. So for instance, you can avoid rebuffers by downloading a worse quality video and making the video look worse. You can also avoid rebuffers by increasing the play delay. You could download the whole video up front, and then you aren't going to have any interruptions. So what ABR algorithms do is they manage the trade-off between these three different things. The way they're going to do that is we take the video and we split the video up into chunks of a couple seconds each. The chunks are encoded at a bunch of different bit rates, from something that's relatively large to something that's relatively small. The ABR algorithm is going to go through chunk by chunk and pick a bit rate for each chunk. And so when you watch the video, maybe it'll look good for a couple seconds and then look bad for a couple seconds, and then it'll look good again. So the reason we go to all of this trouble with ABR algorithms is because QoE matters. I'm sure you can think about times when you've been watching a video at home, and maybe there's been a lot of rebuffers. Maybe the video has looked really bad, and maybe this is annoying and frustrating. Well, there are studies that show it is, in fact, annoying and frustrating. There are also studies that show that if you increase the amount of play delay or you increase the amount of rebuffering, people will watch less video. There are also experiments that are typically not published, but you can find out by talking about to various executives at various streaming services, where if you can improve QoE, you can improve customer retention. And so everyone in this video ecosystem cares about QoE, from the companies that serve the video to you and I that watch the video. So ABR algorithms exist to optimize QoE when throughput is low, but what about when throughput is high, and in fact higher than the bitrate? So in this case, video is going to become bursty. So here we've got the throughput over time during the video. The throughput is higher than the bitrate, which is this line here. So what happens during the on period, we're downloading faster than we're watching, the playback buffer is going to grow. At some point, the buffer is going to become full at this point here. We're going to stop downloading, and this is going to give us an off period. And so we're going to have this on-off behavior of video traffic whenever the throughput is higher than the bitrate. So one other thing to mention here is that as the throughput gets faster and faster relative to the bitrate, the video is going to become more and more bursty, right? We'll fill up that buffer faster, then we'll pause for longer while we wait for it to drain. So video today is much more bursty than it has been in the past. So this graph, the x-axis here is the year, it's the past decade or so. The y-axis is the speed in megabits per second. And what I've drawn here is the average US home internet speed over the past decade. In 2010, it was about 5 megabits per second. And today it's 200 megabits per second, so quite a bit faster. We can compare this to video bit rates, and throughputs. Video bit rates have actually not changed all of that much over the past decade. So back in 2010, your average HD high quality video was maybe 5 to 10 megabits per second. Since then, the industry has invested a lot in video encoding technology. And so an HD video will be 1 to 2 megabits per second. And even a 4K video will be 10 megabits per second, maybe 25 megabits per second if you're Apple. And so there's a pretty big difference here. There's a difference in a factor of about 20 between the throughput that we're downloading and the bitrate of the video on average. So what this means is that video is very bursty today. So one thing I should mention here, so I've grabbed the average US home internet speeds, and this is because the data is very available for the past decade. There's obviously many other places on Earth aside from the US, and they also have internet, and we care about them. There's just less data to graph. The trend here, though, is that the internet is getting faster than the bitrate. So now I want to make this case to you that this burstiness is undesirable behavior of video traffic. And to do this, I'm going to have to introduce this idea called congestion. So just like on a highway, when the highway gets congested because you have too many cars, networks are going to get congested if we send faster than their capacity. Their capacity is sort of how fast they can send data. So if we do this, what's going to happen is data is going to queue up at the slowest part of the network. This will probably be your home router, and it's going to be wait to be sent. So this causes congestion. It causes an increase in delay. Data is going to take longer to get through the network. It causes an increase in loss because queues fill up. There's no room to put the data in the queue. The data has to be thrown out and then resent later. And then finally, if one person is sort of hogging all of the bandwidth, there's going to be less bandwidth available for all of the other neighbors that want to do stuff on the internet. And so this is the real reason why we care about congestion on the internet. It's not that I am sending too fast and causing problems for myself. It's that I am sending too fast and I'm hurting myself, and I'm also hurting everyone else that's sharing the same network. So we have these algorithms which are called congestion control algorithms. And like you would expect from them, the name, they're there to avoid congestion. So these algorithms typically only know about things like how fast they're sending and whether or not they're causing congestion. And so at a very, very high level, the way these algorithms will work, well, they will send faster and faster until they cause some congestion, at which point they'll slow down and they'll repeat. And so just as part of the way that they work, congestion control algorithms will tend to cause a little bit of congestion. Because of this, when we have this bursty behavior of video traffic, it's going to lead to congestion. So during these on periods, we're going to have increased queuing delay and increased packet loss for all of the traffic that's using the network. There will also be less bandwidth available for the neighbors than if the video session wasn't there. So one thing we can do here, we could imagine what would happen if we had a Zoom call that, say, started at the beginning and ran through the end of the video. So during these periods of congestion, that Zoom call would also see higher delay. And so maybe it would be interrupted a bit. Maybe it would break up. Maybe the audio would get choppy. The other thing the Zoom call has to do is it has to pick its own throughput. The throughput that that call could get would be lower during these on periods and higher during these off periods, and it'll vary back and forth. So one thing we could do about this is we could smooth out video throughput. So here we've got video traffic today. There's some congestion. We could smooth this out. We could reduce the throughput below the capacity. And here we would avoid congestion. I didn't actually forget to put anything on that graph. There's actually just nothing on that graph at all because we're sending slower than the capacity of the network. So here we've actually preserved the total number of bits that we're downloading, which will be relevant later. Another thing we could do, we could smooth out even more. We could smooth down to the bit rate of the video. We're still preserving the number of bits. And again, we're avoiding congestion. We've also avoided the on-off behavior of video traffic. And so a Zoom call, say, would see less variable throughput. Great. So this is not a new observation. There's been a whole bunch of work on this before, the smoothing out video traffic. The one thing this work hasn't looked at before is to make sure video still works well when you smooth it out. So I think it's pretty easy to see that you can make video traffic very friendly to its neighbors by not sending any bits at all. But if you did this, you couldn't watch any video, and video is like 75% of the internet. It might also be clear that if you smooth the throughput below the bitrate of the video, this is going to make QoE worse because the ABR algorithms are going to have to adapt somehow to avoid rebuffers. Maybe they would decrease the bitrate. Something that might be more surprising, though, is that if you smooth above the bitrate of the video, this can still make QoE worse. So this is because of the way ABR algorithms work. And so let me tell you about a simple ABR algorithm here. So we're downloading these chunks from the internet. We're going to measure the throughput that we get when we download each chunk. And we're going to pick the highest bitrate, which is less than half of that average throughput. So if in the future we get throughputs which are equal to the average, we're going to be picking bit rates which are half of the throughput. So the buffer is going to grow. We can avoid rebuffers. So now let's imagine we smooth things out. So we're going to reduce the chunk throughput to 1.5 times the bitrate. So what's going to happen? So we start at some bitrate here. This is 10 megabits per second. We're going to get a throughput in the next step of 1.5 times that bitrate, or 15 megabits per second. Then we're going to go and we're going to pick our next bitrate. We're picking half of the throughput, which is half of 15 megabits per second, which is 7.5 megabits per second. And the important thing here is that this number is lower than the bitrate that we started with. And so we're going to be switching down in quality. And then we're going to do this over and over and over again until we wind up in the lowest possible quality. And so here we smooth things out. We smooth things out to something higher than the bitrate. It seems like the ABR algorithm should still work, but in fact, it's not going to. So the observation we make in this paper is that video traffic can be smoother, and it can be smoother without sacrificing any QoE. So over here on the left, we have video traffic today. Over here on the right, we've smoothed things out. So this gray bar here, this is the time it takes for the video to start. After the video starts, we've reduced the throughput down to the bitrate. So what happens to the buffer? In both cases, at the beginning, we're downloading quickly, so the buffer is going to grow. And then over here on the right, we're downloading just at the same rate that we're watching the video, and so the buffer is not going to change at all. So there's sort of two benefits here. One is we're avoiding congestion, but two, the QoE is the same. So there's those three things we care about with QoE. The first one is start play delay. That's just the width of this gray bar, which is the same in both cases. A rebuffer happens when the buffer goes to 0, and in both cases, the buffer is staying above 0. And then finally, the bitrate is the same in both of these sessions. You can see this because we're downloading the same number of bits. That's the area in this gray bar. And I've just sort of drawn this so that the area is the same in both cases. Great. So now I can tell you about our paper. So in this paper, we take this observation and we apply it at scale. So the first thing we do is we introduce a mechanism which allows us to smooth out video traffic. Then we design an algorithm, which is called SAMI, that both picks bit rates and also smooths out video traffic. And then finally, we're going to implement and run experiments with our algorithm where it's going to reduce chunk throughput while actually slightly improving video QoE. So let me tell you about our mechanism. So our mechanism is called application-informed pacing. So basically what's going to happen, you have your video client over here on the left. You're going to ask for a chunk of video from the server. And you're also going to ask for an upper limit on how fast the server is going to send, say 1 megabit per second. And then the server is going to send you that chunk of video, and it's going to send no faster than 1 megabit every second. So if you're familiar with TCP pacing, application-informed pacing is based on TCP pacing. So TCP pacing, we picked this pace rate, this delay. This is an old idea dating back to a thesis of Janie Ho in 1995, and it's now part of the standard congestion control toolbox today. The major difference to TCP pacing is with TCP pacing, the rate is picked by these congestion control algorithms. And the main goal is to smooth out the bursts, reduce the variability in the sending rate, but to keep that sending rate above the average throughput that the congestion control algorithm is picking. With application-informed pacing, the application is picking the rate, and ideally it's going to be picking a rate way below the capacity of the network. And the real challenge with it is going to be how do we go about picking the rate? And I'll tell you about that in a second. One thing I wanted to highlight about this mechanism is this is a very deployable thing. Like this is something you can do today. It's supported by Linux. It's supported by major CDNs like Akamai and Fastly. We're going to talk about experiments at Netflix. Like this is a thing you can use. So how do we pick a rate? So the reason this is challenging is because ABR algorithms measure throughput, and they use this to say something about the available bandwidth of the network. So we just saw this algorithm where we're picking a bit rate less than half of this throughput measurement. You could imagine a more complicated algorithm where, say, we estimate the throughput, we run some simulations, and then we pick something that gives us good QoE in those simulations. So both of these algorithms rely on this throughput estimate, and it seems like the better you could do at estimating throughput, the better you could do in these algorithms. And this is actually a pretty common assumption in papers. People will say things like, I have this mechanism to do throughput estimation, but if you could improve on this mechanism, well, you could improve on our whole system performance. So with pacing, so the problem with pacing is that ABR algorithms are not going to measure the available bandwidth of the network. They're going to measure the pace rates that we pick. And so if we pick a rate of 1 megabit per second, we're not going to learn anything about whether the network could do 2 or 100 megabits per second. So the idea in this paper is that these algorithms don't actually need these precise estimates of the network throughput. So here's an example. So let's say the bit rates we have are 0.5 megabit per second and 1 megabit per second. And you're an ABR algorithm, you want to pick a bit rate. And the question is, do you need to know exactly what the throughput is? And let's say I promised you that the network is somewhere above 100 megabits per second. So in this case, when you download 1 second of this top bit rate, it'll take you less than 10 milliseconds. So this is really fast. And your typical video bit rate is going to be about 1,000 or 10,000 times larger than this. And so this will be nearly a rounding error on the size of the buffer that you have. And so because of this, you don't need to know if it's like 100 or 101 megabits per second. You're just going to pick the top bit rate. So more formally, what we're saying here is that ABR algorithms implicitly solve this decision problem. And the decision is the throughput high enough to pick the bitrate or is it not? So we've seen this algorithm a couple of times before. The decision equivalent of it is to say, is the average throughput at least as high as 2 times the bitrate? If it's anything above that level, we'll pick the highest bitrate. And so what this allows us to do is if we want the AVR algorithm to make the same decision, we can actually use pacing to smooth out the throughput down to this level of 2 times the bitrate. And if we do, the AVR algorithm should make the same decision. Great, so now I can tell you about our algorithm. Our algorithm is called SAMI. It's called SAMI because SAMI is the current world record holder for world's fastest snail. We're sort of slowing things down, but it's still good. So SAMI is split up into 2 different algorithms. There's an algorithm for the initial phase, which is before video playback starts. And there's an algorithm for the playing phase, which is after playback starts. We have these 2 different algorithms because the goals we have are different. Before we start playing, we care about how long it takes to start playing. After we start playing, we no longer care about that. So in the initial phase, we actually don't do any smoothing or pacing at all. And the reason for this is that we're going to be implementing this algorithm at Netflix. And at Netflix, the initial phase is maybe at most a couple of seconds out of an hour or more of video. And so it's going to be a very small fraction of overall traffic. If you were in another setting, like let's say TikTok, the initial phase might be a larger fraction of the video, and we could do some more stuff here. So the one thing we do have to do in the initial phase is to make the very first bitrate selection. So the reason this is challenging is because we haven't downloaded any chunks yet, and so we don't yet have any throughput measurements to use for that. So there's many ways that people approach this in the literature. You can do all kinds of stuff with like TCP statistics. What people often do in practice is you use historical throughput estimates from, say, the last 10 hours that you were watching Netflix to make this decision. So the one problem with doing this is if you use pacing, that will reduce these throughput estimates from previous sessions, and that can cause you to make different decisions in this session. And we actually saw cases when we would do pacing and we wind up with lower initial quality. So we do a whole bunch of work here to make sure the estimates for the throughput in the initial phase come only from the previous initial phases, and that's all we do. So in the playing phase, what we're going to have to do, so we have some ABR algorithm, and we analyze this ABR algorithm to figure out how much throughput that ABR algorithm needs to pick the highest video quality. So I've sketched this here. This is this gray bar here, and typically it's a function of the size of the buffer that the player has accumulated. So we need to pick a pacing rate. What we do is we just pick a pacing rate which is somewhere above this function. We tune this experimentally, and what we get is about 3.5 times the bitrate when the buffer is low and 2.5 times when the buffer is high. So now let me tell you about how this behaves. So what we're going to do, we're going to look at a standard Netflix session. We're going to call this the control traffic. Then we're going to compare this to a session which runs SAMI. This is in the lab. It's a 40 megabit per second link, a 3 BDP queue size, a 10 millisecond round trip time, and the control will run TCP Reno. So this is the way the control traffic behaves. So the x-axis here is the time in seconds. The y-axis is the throughput, and the capacity of the network is 40 megabits per second. So in the beginning, the control traffic is downloading as fast as it can. And then it switches to this on-off behavior later in the session when the buffer has filled up. We can also look at the round trip time. This is the time it takes data to go from the video client to the server and back again. The round trip time has a base of 10 milliseconds, which is that sort of invisible line at the bottom of the graph. And then every time the round trip time is higher, it's because we've built up some queuing delay because of congestion. So because TCP is sending quickly at the beginning, we have a bunch of queuing delay. And then during these on-off periods, we're still sending quickly, and so we still have some queuing delay. This is what SAMI does. So at the beginning, we have high throughput, and then immediately after we start playing, we decrease the throughput, and we continue to decrease it over the rest of the session as we build up more buffer. Over on the right-hand side, this is the round trip time. Again, it's high at the beginning because we're sending quickly. We have a little bit of congestion. And then after that, the round trip time is pretty much flat. So let's look at how this impacts neighboring traffic. So what we're going to do, we're going to start some neighboring traffic and look at its performance. What you would expect to see is lower queuing delay because the round trip time is lower. And you would also expect to see higher throughput. The reason for this, the fair share throughput that it would get, the neighboring traffic would get with the control algorithm is about 20 megabits per second. And SAMI is giving more than 20 megabits per second to this neighbor. Great. So for UDP and TCP, these are just standard protocols. We see, like we expect, lower delay and higher throughput. For HTTP response time, we're just downloading web pages periodically in the background, and SAMI's improving performance by about 20%. We also start another video session in the background. SAMI is improving the play delay for that video by about 5%. I wanted to kind of illustrate this a bit better, so here's a lab experiment with Zoom. So what we're going to do, we're going to start a Netflix video. We're going to switch to Zoom, and we're going to watch a video stream via Zoom. I've sort of set this up in a little contrived way. So the network has an extremely large queue, about 10 seconds. And this is going to mean that without SAMI, we're going to get occasionally large queuing delay. For Zoom, this is going to interrupt the video. The snail is going to move in this kind of weird herky-jerky way. So SAMI is going to avoid the queuing delay. And because of this, the snail is going to move more smoothly. Great, so here's the two videos. So two things to notice. One is over here on the right, we have the round trip time during the test, and then we'll do one here too. The other thing to notice is right at the beginning, there'll be some text. It's the SAMI, the snail text. The top one, you'll be able to see a pause right away. Okay, so let's watch it. Great, so we're starting our video. And then we're gonna switch over to Zoom. Great, and so the text just paused up top. And so now what to look at is maybe the top of this shell here and compare it to the top of this shell down here. It's a little subtle, but if you look at the top, it sort of freezes and freezes and freezes. And if you look at the one in the bottom, it's just kind of moving smoothly along. Great, so now let me tell you about the experiments we ran. So we ran experiments with Netflix. And the reason for this is that Netflix is the largest application today on the internet. It's about 10% of all the bytes on the internet. So this gives us a lot of data to use for experiments, but also if we can do things to make this friendlier, this will be a good thing for the internet. So the experiments we're going to talk about are called A/B tests. What we have here is a bunch of Netflix users. We're randomly assigning them to either treatment, which runs SAMI, or control, which runs Netflix's current algorithm. We're going to collect a bunch of data about performance, and then we're going to compare the outcomes. So if we see that there's higher QoE here than there is here, we're going to say things like SAMI improves performance. The experiments, so you might know these not as A/B tests, you might know them as like randomized controlled trials in medicine. It's just your typical random experiment. So the experiments we have here, they're relatively large. It's less than 1% of Netflix traffic. We ran these experiments for about 2 weeks. We tried many different combinations of parameters here, which pace rates to pick, et cetera. And in total, we had about 11,000 years of video in these experiments. So these are the results for congestion-related metrics. So this first metric is chunk throughput. This is how fast SAMI is, or sorry, how fast Netflix is sending data when it is sending data. And with SAMI, it's about 62% lower. This next metric is retransmissions. So when queues fill up and packets are lost, they need to be retransmitted. If SAMI can keep those queues lower, we can avoid retransmissions. And SAMI is reducing retransmissions here by about 50%. Round trip times. So when those queues fill up, the round trip time will go up. If SAMI can keep the queues lower, the round trip times will go down. And SAMI is reducing round trip times by about 20%. We can also look here at the video quality. So these first two metrics are video quality during the entire session and right at the beginning. It's very slightly higher, like 0.05% higher. This next metric is play delay. It's about 1% lower. And then there is no significant impact on rebuffers. And so this is not like a major QoE improvement. I want to emphasize that it's a very minor QoE improvement. It's actually coming from not that we're smoothing out the video traffic, but it's coming from these changes we made to the initial part of the session using the initial throughput and so on. The thing I really want to highlight here, though, is that we're reducing congestion. We're sending a lot slower, and we're doing this without making video QoE worse. So there's a lot more we can do here in the future. We can talk more about this later. One thing I'm really excited about doing, though, is trying to measure the impact of SAMI on other traffic on the internet. For instance, maybe we could run SAMI at Netflix and then look at the impact on non-Netflix traffic, for instance, Zoom. So we saw some lab experiments about this, but we haven't seen anything about how this would work in practice. So the question that we had was, how could we go about running an experiment like this? And this will lead us to the next chapter on unbiased experiments in congested networks. So this is joint work with Veronica, Shravya, TY, Nick, and Ramesh. We presented it at IMC in 2021, and it was awarded the 2022 Applied Networking Research Prize. So we just saw A/B tests. We use them to evaluate SAMI. A/B tests are super widely used in networking to evaluate new algorithms. So here are just a couple of major papers of the last decade. Some of them are pretty major papers, like more than 100 citations, maybe 1,000 citations, and all of them rely on A/B tests to argue that their new algorithm is better than what was there before. So the particular way we're using A/B tests here is we're using them to generalize. We're making decisions about deploying a new algorithm based on the results of a small scale test, like the SAMI one I showed you was less than 1% of traffic. So this is a generalization and it requires assumptions. And one of the assumptions is that the outcome of one unit in the test doesn't depend on the other units in the test. When it does, this is called interference, and interference can bias the results of A/B tests. So if we think about it for like 5 seconds, it should be clear that interference exists in congested networks. If you have some treatment algorithm and it works really great, but the reason it works really great is because it's hogging all the bandwidth from the control algorithm, then this is going to bias the results of your test. So in this paper, what we show is that interference can make A/B tests extremely misleading. And so I'd like to tell you about the experiment we ran to demonstrate this. So the treatment for this experiment was called bitrate capping. So back at the beginning of COVID-19, governments around the world asked large streaming services like Netflix and YouTube to reduce their load on the internet. So the way they did this, they asked them to send less data. They placed an upper limit on the video quality that they would send, sort of a cap on the bitrate. And so the goal here was to reduce the internet traffic by about 25%, avoid some congestion when we were all working from home and all sort of relying on the internet. So we wanted to see what were the effects of this bitrate capping on congestion. And so we ran an A/B test, and what we saw in the A/B test, so these first 3 metrics, these are those congestion-related metrics we were just talking about. And in the A/B test, the congestion-related metrics seemed to get worse. Bitrate got lower, but this was expected because we were reducing bitrates. And then there was no change in either rebuffers or play delay. And so in this experiment, it somehow looked like we sent less data into this congested network and congestion somehow got worse. This is weird. So let's look a little closer. So let's say we've got some network here and this network is congested. And what we're going to do, we're going to apply bitrate capping. We're going to send less stuff into the network and the network's going to become uncongested. So there's 2 effects of bitrate capping here. The first effect is we're using 50% less bandwidth. And the second effect is that we have no congestion. So in an A/B test, what we're going to do, we're going to take all of the traffic to that network, split it into 2 groups, apply bitrate capping to one group and nothing to the other group. So one possibility here is that bitrate capping is going to reduce congestion, right? There's some free space now in the network. So in the A/B test, we're going to compare here treatment to control, and we're going to see that treatment is using about 50% less bandwidth. But here, the level of congestion is the same, and we're not going to see any impact on congestion in the test. And this is because both of the traffic is using the same network, and that network is not congested. So here's another possibility. So the control traffic is going to be running this congestion control algorithm. Maybe it notices there's some free space in the network. It'll start to send faster, and the network's going to remain congested. So now when we compare treatment and control, treatment is using about 1/3 as much less bandwidth as it was before. And so we've gotten the value of that estimate wrong. And again, when we compare treatment and control and look at the effect on congestion, they're using the same network, and that network is going to be congested. So we have this interference between the treatment and control that's causing us to miss this impact on congestion. So this is sort of concerning, right? We run A/B tests to figure out what happens with algorithms, and we had this algorithm to reduce congestion, and we ran this A/B test and we see no impact on congestion. So here's the experiment we ran to sort of work around this. So we found this pair of networks. They were both located inside of Netflix. There's a bunch of servers and routers, and they were connected to some ISP. You could think about this as like a provider like Comcast, although it wasn't Comcast in this test. The one thing to highlight is we ran some pre-experiment differences between these two, and we saw no major differences in any of the metrics we're going to talk about here. So, okay, so what do we want to do? So we want to do mostly bitrate capping and treatment, mostly not bitrate capping and control, compare the 2 of them and see what happens when we do bitrate capping. So we did this. In network 1, we capped 95% of traffic. In network 2, we capped 5% of traffic, and so we can compare these 2 to see the effects of bitrate capping. The other thing this lets us do is now we have two A/B tests, and we can compare the results of those A/B tests to the effects of bitrate capping. So here we've got this 95.5 test, and here we have this 595 test. So here were the results. So these first two are these congestion-related metrics, round trip time and throughput, and we saw improvements in our experiment. We also saw a reduction in play delay in our experiment when we compared one network to the other. But when we looked at the A/B test didn't just get this value wrong, it actually got the direction wrong. So what looked like in the A/B test, congestion getting worse, was actually an improvement in congestion. And so if we had relied only on the A/B test, we would have been very misled about the results of this experiment. So this is kind of concerning because we use A/B tests everywhere in networking research. And to sort of drive this home, I wanted to tell you a bit of a cautionary tale. So back in 2016, Google released this congestion control algorithm called BBR, and they were very, very excited about it. They said things like, we're finally doing congestion control based on congestion. They advertised that they got less congestion and that they got higher throughput. And they backed this up with A/B tests. Like in experiments, they saw that throughput was 2 to 25 times higher than cubic. They also saw reductions in round trip times by 50 to 80%. And so they were very excited about this. They published this algorithm, and people started looking into it. In academia, we spent the next couple of years just dunking on BBR because it turned out that BBR was not fair. And what I mean by this is if you had 16 cubic algorithms, which was the then standard, and one BBR algorithm, and you had them compete with each other for network resources, that one BBR algorithm would get almost half of the network bandwidth and leave the other half for those other 16 algorithms to compete among themselves. So this was pretty egregious, and it even made it onto Vice.com. And you really don't want your congestion control algorithm to ever make it onto Vice.com. So great. So I don't work at Google. I am not familiar with these experiments. I don't know what happened here. But one possibility is that this was interference. Like the reason this algorithm looked so good in this experiment was because it was stealing a bunch of throughput from the other cubic algorithms that were running on the internet. Great. So this is concerning. And the other thing we highlight in this paper is that we can run experiments that reduce the bias. So we've seen some so far. I wanted to tell you about just one other type of experiment, which is called an event study. So basically, you're running your control for a while. At some point, you have this event, you switch to treatment, and then you compare after to before to see the effects of the treatment. So this is a sort of thing you probably do all the time in your own life. Like you try out something new, you see how it works, see how it makes you feel. The reason this avoids interference is because they're not running at the same time, right? So they have no way to interact with each other. There are other types of experiments, and we talk more about them in the paper. I'm happy to talk more about them offline. And so there's a lot more we can do here. So we could look more into this experiment stuff. We could try and design new experiments. We could try out new and old algorithms with these experiments. But the thing I'm really excited about here is we could use this technique to look at how SAMI impacts other traffic on the internet. And so what we would do, we would run an event study at, say, Netflix. We'd call up our friends at Zoom or YouTube or Fastly or wherever, and we'd say, hey, what did you see? And they would say, oh, things got better, things got worse. And then we could know something about how SAMI impacts the rest of the internet. Great. So that was the thesis. We looked at 3 different parts: smoothing out video traffic to make it a friendlier neighbor. How do we run experiments with algorithms like SAMI that impact all of the traffic on the internet? And then we didn't look at this 3rd part. So I wanted to back up a little bit for the ending and talk a little bit more about congestion more broadly. So what we've seen here are 2 different ways of reducing congestion. One is to smooth out video traffic, and the other is to cap video bit rates. If we compare this to the typical way that we control congestion and reduce congestion on the internet, these are actually pretty unusual approaches. And so I wanted to tell you a bit more about how we do things today. So what are we trying to do in congestion control? Well, we're trying to send data over the internet. The problem with doing this is, here's a quote from a textbook on congestion control. It came out last year by Peterson, Brackmo, and Davey. They say, at the core of the internet is a thorny challenge: how the internet's resources are best allocated to all the competing interests trying to use it. So here, the problem of congestion control, it's a resource allocation problem among competitors. So we're looking to get a best allocation. In congestion control, the best allocation is typically one that maximizes throughput. So here's the very first paper of congestion control research by Jacobson and Carrolls in 1998. The situation they're describing here, you and I are sharing a network. We're both sending about half the speed of that network. And they say, well, if you stop sending and I'm sending only half the network, now I'm wasting bandwidth, and so I should send faster. Here's another quote. This is a paper of Frank Kelly in 1997. This is like a pretty major theoretical modeling paper about how these congestion controls interact with each other. They introduced this idea of utility functions, which is sort of the value that a congestion control algorithm gets out of some throughput X. And the assumption here is that if your throughput is higher, you're going to do better. Finally, here's another quote from this textbook. They're saying, what do we want out of congestion control algorithms? And they say, clearly, we want as much throughput and as little delay as possible. The other thing about that quote is it's a competition. Congestion control algorithms are competing with themselves for this scarce bandwidth of the internet. And in particular, they're competing in a way which is a zero-sum game. So when we have a congestion control algorithm, like we were just talking about with BBR, that uses more bandwidth when it competes with other algorithms, we call this unfair. And we sort of assign a moral tone to it. We say it's bad to be unfair, because if we use more throughput, this means our competitors get less throughput, and they're going to be worse off because we want to maximize throughput. So this is the way we do congestion control. This is the way we've done congestion control for a while. This is how we would teach congestion control in an intro to networking class. So let's back up a bit. So what are we trying to do here? So what we're trying to do, according to congestion control, would be to send data over the internet. But if we think about it, like, surely this is not what we want to do online, right? We want to do stuff. We want to maybe watch video. This is 75% of the internet traffic. Maybe we want to buy things or play games online or talk to our friends on social networks. We have all these things we want to do out of the internet that are much more than sending data over the internet. And so because of this, what we do in our work is we start from video traffic and we look at what video traffic needs for good performance. For video traffic, we know what this is, and it's that the video traffic gets good QoE. And so because of this, we can avoid a bunch of the assumptions that typical congestion control work has. So for instance, one of our goals in this paper is to get low throughput as we can get. And the reason is because we have video traffic, and we just saw that video traffic doesn't need maximal throughput to get good QoE. We're also not in a zero-sum game here, right? Video traffic in our experiments gives up throughputs to its neighbors, and we don't see any impact on QoE. So we're not zero-sum. And in fact, in lab experiments, we saw improvements to the QoE of the neighbors. And so we're really not zero-sum. So what we're kind of doing here is, because we know all this stuff about video, we can kind of shift the mindset from one of competition and algorithms competing with each other to one of friendliness and how we can improve the performance for video's neighbors. So this is going to be good for everyone if we can do this. So certainly it's going to be good for non-video traffic that's sharing the same networks. We saw some experiments with this in the lab, and I would love to run some larger experiments with this on the internet. The thing is, though, this is not just us in academia sitting down and being like, ooh, wouldn't it be nice to be nice? We should be nice. Like, even if you work for a streaming service and the only thing you care about is your own QoE, you're still going to be incentivized to be friendly. So why is this? So one is that the video queue is not getting worse. There's sort of no cost to the service to be friendly. And the second one is that imagine me and my roommate are at home and we're both watching Netflix on our own separate rooms. If I'm friendly and this improves things for my roommate, and my roommate is friendly and this improves things for me, well, this is going to improve things for both of us, and it'll improve things in particular for Netflix. And so if Netflix is 10% of the internet, there's probably a bunch of cases when it's sharing the network with itself. And so because of this, I think the future of internet traffic and internet research is maybe to make things friendlier. So we can look at other applications, like we could look at Zoom, we could look at web browsing, we could look at gaming, and we could do things to make these applications friendlier too. We could also do more to make video traffic friendlier. We could try and reduce pace rates closer to the bit rates. We could look at other networks, slower networks, and make things friendlier there too. One thing I'm pretty excited about here is we could start from what video needs for good performance, and we could design one algorithm that sort of does all of the stuff that we've talked about so far. So we could have an algorithm that does congestion control and fixed bit rates and is also friendly to the neighbors on the internet. And so with that, I'm done. Let's make internet traffic friendlier.